One of the prominent, furthermore undeniable, physicists has discussed his evaluation with regards to this issue. Michio Kaku, recognized for his excellent contributions to the fields of physics, has recently affirmed that the James Webb Space Telescope has discovered 6 colossal galaxies that scientists previously thought could not exist. These findings have the potential to open up new perspectives in our scientific understanding of the universe. It is therefore intriguing and worth watching for the developments that arise. Kaku is an esteemed figure in the scientific community. As a physicist of American and Japanese heritage, he is seen as an expert in both classical experimental physics and quantum mechanics. Unlike some more conservative and cautious researchers, Kaku does not belong to that group and has been open to the astonishing results of the James Webb Space Telescope mission. We are pleased that this distinguished scientist has chosen to break his silence and openly share what can no longer be denied. The excitement and intensely focused tone of the renowned physicist are clear in his comments on the discovery made by the James Webb Space Telescope, expressing that this revelation has been the highlight that has piqued his curiosity. Join us as we explore the implications of Michio Kaku's revelation of these 6 massive galaxies. Kaku is a scientist who has always been willing to consider new theories throughout his life. He knows that Einstein's theories of relativity and Newton's laws are insufficient to capture the full complexity of the universe. Kaku understands that the discoveries made by the new telescope have the potential to enhance the scientific field, even though many of his peers have not been willing to embrace this view. This has caused concern and insomnia among proponents and opponents of quantum mechanics. However, this only provokes laughter from Kaku. The James Webb Space Telescope has revealed the discovery of 6 massive galaxies dating back to the earliest epochs of the universe. Each of these galaxies contains more stars than our Milky Way, despite having formed just a few 100 million years after the Big Bang. The team of astronomers who made the discovery has named these unusual galaxies universe breakers because their existence would reshape our entire understanding of the universe. Something no longer fits here. The Big Bang theory tells us that the universe was a chaotic mess after the initial event. The first solid objects took many centuries to form, and it took countless additional years for them to reach sufficient density and emit light. The formation of complex structures like galaxies was expected to happen much later. Some of the newly discovered galaxies surpass the Milky Way in size, and their immense luminosity suggests that they were likely forming many new stars each year, whereas our galaxy forms stars only intermittently. It remains unclear exactly when the first galaxies formed, as scientists have not been able to determine this until now. The only thing that is certain is that initially, there may have been only single stars or groups of stars, which eventually came together to form increasingly larger structures. Gradually, this led to the formation of dwarf galaxies, which experienced mergers and slowly grew. According to previous theories, highly organized and massive galaxies could not have existed at that time, which raises the question of whether the universe is much older than previously believed, or whether complex toroidal structures developed significantly earlier. This situation is challenging for conventional science, which still struggles with this model. Some areas of physics have strongly refused to accept this discovery, citing potential errors in the age calculations. Kaku is aware of this and had this to say. There are numerous instances of outdated and misleading theories that stubbornly persist due to the prominence of certain researchers. Many of these theories were eventually disproven when critical research revealed their flaws. Therefore, the key work in any science, particularly in physics, lies with the experimentalists who uphold scientific truth. In fact, on Earth, we have virtually no knowledge of the true origins of the universe. The Big Bang theory was established in 1927, based on observations of the universe's expansion. This data led to the conclusion that the universe began from a single point and has been expanding ever since. At the time, it was difficult for people and scientists to imagine a universe with a beginning and an end. The idea of a universe that had always existed and was infinite in time was beyond human imagination. Even today, scientists still struggle to fully comprehend this. However, it is essential to reconsider these possibilities. These new observations do not align at all with what scientists have long relied on in the Big Bang theory. Yet, science has shown time and again that reevaluation and openness to new ideas are essential components of the scientific process, just as much as the confirmation of certain theories and observations. When Einstein was young, it was believed that the stars and planets were firmly fixed in the universe in these specific arrangements. Consumed and characterized, space has always intrigued us. Now we realize that everything in the universe is moving. Planets circle stars, which move inside their galaxies at numerous kilometers per second, and entire galaxies move rapidly through the universe, whose fate we cannot yet predict. Today, scientists are challenged to accept uncomfortable truths, and it is understood that theories are not mere guesses or absolute facts. Truths remain uncertain until they are thoroughly tested or confirmed by careful observations. The concept of the Big Bang arose from the realization that galaxies are moving away from each other, and this distance is relative to their separation from Earth. This observation, known as Hubble's law, suggested that the universe was expanding. For some time, phenomena like cosmic microwave background radiation and the redshift of light from distant galaxies and other cosmological structures seem to support this theory. However, it is important to remember that, in the past, people who believed the Earth was flat or that the Sun orbited around us also had their own kinds of evidence. Eventually, breakthroughs or technological advancements offered a clearer and more accurate picture. Today, we face a similar situation. Scientists expected the new James Webb Space Telescope, JWST, to confirm assumptions related to the Big Bang, but instead, it has discovered 6 galaxies that seem impossible. This reminds us that science is constantly evolving, and scientists must remain open to new discoveries and be willing to revise existing theories based on available evidence. Researchers use redshift as a tool to determine certain quantities in the study of the universe. Redshift, also known as the Doppler effect, refers to the change in the color of light as the light source and observer move relative to one another. To understand this, imagine standing still and watching a car approach you. As the car moves closer, the engine noise grows louder. However, once the car passes you or moves away, the engine sound changes. This is because the sound frequency varies as the car moves. The same is true for light. When a light source, such as a distant star, moves toward us, the light we see shifts toward bluer tones. Conversely, when the light source moves away from us, the light shifts toward redder hues. This phenomenon is called redshift. Physicists have converted redshift values into velocities and distances for measurements in the study of the universe. However, it is important to note that small errors in these measurements could have significant impacts. The estimation methods previously used are currently under review, and it will be interesting to see what results researchers arrive at concerning the latest findings related to our universe. It is essential to consider whether these results are genuinely due to redshift errors or whether some researchers are merely denying the facts. This is a question that requires thorough examination and careful review of the data and methods used in research. As scientific inquiry progresses, the discoveries made by instruments like the James Webb Space Telescope frequently challenge our assumptions about the universe. The recent discovery of 6 colossal galaxies, dating back to the early epochs of the universe, is one such example. These galaxies, which defy conventional theories of galaxy formation, raise significant questions about the timeline and mechanisms involved in the evolution of cosmic structures. The James Webb Space Telescope, a successor to the Hubble Space Telescope, is equipped with advanced technologies that allow it to peer deeper into space and observe with exceptional clarity. Its ability to detect light from the farthest reaches of the universe provides astronomers with a window into the past, allowing them to study galaxies that formed billions of years ago. The discovery of these ancient and massive galaxies challenges existing models, which predict that such large structures should have formed much later in the universe's history. The implications of these discoveries extend beyond astronomy and into the realm of fundamental physics, forcing researchers to reconsider established theories about the early universe, including the Big Bang theory, which posits that the universe began from a single point and has been expanding ever since. While observational evidence, such as the cosmic microwave background radiation and the redshift of distant galaxies, initially supported this theory, the discovery of galaxies that appear too mature for their age complicates this narrative. Michio Kaku, a prominent physicist known for his work in theoretical physics and popular science, has commented on these developments. Kaku, known for his ability to connect complex scientific concepts with public explanations, recognizes the groundbreaking potential of the JWST discoveries. Unlike some of his more skeptical colleagues, Kaku embraces the idea that revolutionary observations should prompt revisions in scientific thinking. He has emphasized the importance of empirical evidence in shaping our understanding of the universe, highlighting that theories must continually evolve to accommodate new information. The debate sparked by these discoveries reflects the dynamic nature of scientific inquiry. On one hand, there are proponents who argue that the discovery of early massive galaxies suggests a longer timeline for cosmic evolution than previously thought. This perspective challenges the conventional view that galaxies grow slowly over billions of years through mergers and the gradual accumulation of smaller objects. On the other hand, skeptics caution against prematurely discarding established models based on limited observational data. They advocate for a cautious approach, suggesting that anomalies in data interpretation or measurement errors could explain the surprising findings. Redshift, a phenomenon observed in the light emitted by distant galaxies, is at the heart of this ongoing debate, assumes a significant part in these vast examinations. As universes move away from Earth, the light they emanate shifts towards longer wavelengths, a peculiarity known as redshift. By estimating the level of redshift in a galaxy spectrum, astronomers can surmise its distance from Earth and its speed relative to our own universe. This information is fundamental for building models of cosmic development and understanding the distribution of galaxies in the universe. The James Webb Space Telescope's capacity to identify faint infrared signals allows it to observe galaxies that are otherwise obscured by dust and gas in the early universe. This capability is crucial for considering the formation of stars and galaxies during the universe's earliest stages, a period known as the cosmic dawn. By analyzing the light emitted by these distant galaxies, astronomers can trace the chemical composition of the early universe and gain insights into the processes that drove the formation of the first stars and galaxies. In addition to its vast implications, the discovery of these early massive galaxies raises philosophical questions about the nature of scientific progress and human understanding. Throughout history, scientific principles have shifted in response to new discoveries and observations. What once seemed impossible or hazardous to establish as theory eventually becomes accepted as new evidence emerges. This iterative cycle of hypothesis, observation, and revision is key to the advancement of knowledge in every scientific discipline. The concept of a paradigm shift, as articulated by philosopher Thomas Kuhn, describes the profound change that occurs when anomalies in existing theories prompt a fundamental reevaluation of scientific principles. The discovery of early massive galaxies challenges cosmologists to reconsider their understanding of cosmic evolution and the processes that led to the galaxies we observe today. It underscores the importance of staying open to revolutionary ideas and updating theories based on observational evidence. Cosmologists and astrophysicists are also grappling with the implications of these discoveries for our understanding of dark matter and dark energy. These elusive components, which together constitute the majority of the universe's mass and energy content, play a crucial role in shaping the large-scale structure of the universe. The distribution of galaxies and the rate of cosmic expansion are influenced by the gravitational effects of dark matter, while dark energy is thought to drive the accelerated expansion of the universe. The discovery of early massive galaxies places new constraints on theoretical models of dark matter and dark energy, prompting scientists to refine their understanding of these enigmatic phenomena. In the realm of theoretical physics, the discovery of early massive galaxies has sparked renewed interest in alternative cosmological models. Some theorists propose modifications to the standard cosmological model, such as the introduction of extra dimensions or adjustments to the laws of gravity, to account for the observed anomalies. These theoretical ideas challenge physicists to explore new avenues of research and develop novel theoretical frameworks that can accommodate both established observations and emerging data. The JWST discoveries also have practical implications for future space exploration and the development of advanced astronomical instruments. By pushing the boundaries of observational capabilities, the telescope provides valuable insights into the technical challenges of studying distant galaxies and cosmic phenomena. It serves as a testament to human ingenuity and the collaborative efforts of scientists, engineers, and technicians who design, build, and operate cutting-edge space observatories. Looking forward, cosmologists anticipate further discoveries from the JWST that will continue to reshape our understanding of the universe. Future observations may reveal additional early massive galaxies, shedding light on the diversity of cosmic structures and the processes that govern their formation. These discoveries will inform ongoing efforts to unravel the mysteries of cosmic evolution and deepen our appreciation of the complex interplay of physical forces that shape the universe. In all, the discovery of early massive galaxies by the James Webb Space Telescope represents a milestone in our exploration of the universe's origins and evolution. It challenges existing theories, prompts new questions, and highlights the dynamic nature of scientific discovery. Michio Kaku's perspective on these developments emphasizes the importance of embracing uncertainty and remaining open to surprising discoveries in the pursuit of deeper insights into the cosmos. As humanity continues to probe the mysteries of the universe, each new discovery brings us closer to unraveling the cosmic tapestry that surrounds us.